Now that we've introduced the kinematic equations and started to get some practice in how to use them, it's time to start shifting a little bit more towards the eventual goal of learning about projectile motion. And we're going to start that by first talking about free fall. In order to start this discussion, though, let's think about a question that we've thought about for a very, very long time. Which will fall faster, a heavier object or a lighter object? Now, if we drop them from the same height, let's imagine we have a bowling ball and a feather, and we drop them at the same height, which will hit the ground first? Now, instinctively, you probably know what most people would instantly say, which is what Aristotle first claimed back at around 350 BCE, which is that heavier objects always fall faster than lighter objects. So obviously, the bowling ball will hit the ground first because it is much heavier than a feather. So it will naturally fall faster. And this was the predominant form of thought for a couple thousand years, until eventually, the 1600s, around 1630 CE, we introduced a gentleman known as Galileo Galilei, Italian, who instead said that all objects fall at the same rate in a vacuum. So in fact, if you were to drop the bowling ball and the feather at the same time, they should hit the ground at the same time. Now, at first glance, this may seem a little bit ridiculous, but the reason why Galileo is actually right here is because of this very specific part in a vacuum. If we are in a vacuum, we have removed all other forces from the situation except gravity. And specifically, a vacuum meaning that we have gotten rid of all the air. So there is no air resistance, which we often also call drag. Because what really causes the feather to appear to float downward compared to the bowling ball falling quickly is the fact that air particles are pushing up on the feather as it falls to the ground. You remove those air particles, and they will in fact hit the ground at the same time. And we will see some demonstrations of that in class. So Aristotle, unfortunately, was not correct here, and we actually need to add an addendum to this. The heavier objects always fall faster than lighter objects if air resistance is being taken into account. But even then, it's not even necessarily just the weight that matters. Other things like the surface area and things like that are actually just as important. Ultimately, though, Galileo was the one who came to the correct answer here. Well, if all objects fall through, the space around us at the same rate, as long as there's no air resistance, what is that rate? What is the acceleration, what we call the acceleration due to gravity? Well, we abbreviate the acceleration due to gravity with a lowercase g. So that stands for that exact phrase, the acceleration due to gravity, and a close to exact value is 9.81 meters per second squared down. We'll talk more about the down in a second. This number actually extends past this. It's 9.81, continues onward, but for the sake of argument, we could easily round it off to 9.81 and be correct for 99% of the calculations you'll ever do. Now, you'll notice, though, that this is very close to a number that's, to be frank, much easier to work with, which is 10. And oftentimes, we will just say G is 10 meters per second squared down. In fact, I'm going to go ahead and tell you right now that I will almost universally only use 10 meters per second squared down, because not only is that what the AP test does, but that's what a lot of colleges do too, because it's just faster and easier, and you get much cleaner numbers. Now, for this class, though, I really want to mention that we will use 10 meters per second squared down for everything except for labs. Because labs, we want to be as exact as possible. We want our numbers to be as precise as possible. So in that situation, we'll use 9.81. All other situations, we'll focus on just using 10 meters per second squared down. Now, I want to mention one thing. I hear a lot of people say gravity is 10 meters per second squared down. That's a bit of a misphrase. It's not gravity that is that. It's the acceleration due to gravity, which is 10 meters per second squared down. Now, a couple of things we want to add to this, a couple qualifiers. First off, this acts on all objects on Earth. Every object you see will fall at the same rate, 10 meters per second squared down, as long as there's very negligible air resistance or drag. Additionally, this is always the value near the surface of the Earth. Now, what do we mean by near? Because that is a very vague term. And by near, we really just mean within our atmosphere, within reason. If we get up to really high altitudes, there might be a slight change. But really, for everything we're trying to do, 10 meters per second squared down is a fine approximation for what we're trying to calculate. Lastly, it is always pointed down. Well, what do we mean by down? We mean specifically toward the center of the Earth. Now, we're going to learn more about that later, about why it is toward the center of the Earth, but it is always pointed in that direction. So really, no matter what scenario we're in, wherever down is, that is going to be the direction that gravity is acting. So let's formally define what free fall actually is. We say that an object is in free fall if it is under the influence of gravity, but no other forces. In other words, we're going to ignore all air resistance and drag. In fact, I'm going to go ahead and tell you that you don't need to consider that unless it is being specifically brought up. We can ignore air resistance and drag. Additionally, up to this point, we've only worked with one-dimensional motion side to side. Well, we're going to continue to only work with one-dimensional motion, but rather than having it be a horizontal one-dimensional motion, we're going to work with a vertical one-dimensional motion, up and down being our directions, up and down. Now, specifically, this means that currently we're limited really to just a couple of scenarios. One, taking an object and dropping it because it goes straight down, or taking an object and tossing it vertically straight up so that it comes vertically straight back down. We're not doing anything side to side or being launched or anything like that. Only dropped and thrown straight up and down. That's all we're going to start with for now. So first, let's consider an object that's being dropped. Well, for being dropped, we're saying that initially its velocity is 0, and additionally, as we already said, its acceleration will be g when it's let go, which will be 10 meters per second squared down. So at the instant it's released, that acceleration is g. So we start at a velocity of 0, and it starts to accelerate downwards. So initially it's not going very fast, and as time goes on, it speeds up, speeds up, speeds up until it hits the ground. Now, there's a couple of different ways we could draw graphs for the motion of this sphere, for instance, because it really depends on what we define as positive and negative with regard to up and down. And you may think that's silly. You might naturally think, well, wait a second, wouldn't I always want up to be positive and down to be negative? Well, remember, positive and negative are arbitrary. They're just different directions. And there will actually be scenarios when your math will be easier if you flip those and make down positive and up negative. But if you do that, you just have to remember to be careful. So let's first look through this with the motion. So this is a position versus time graph and a velocity versus time graph for the sphere as it drops. Now you'll notice this is a y, and the reason why it's a y now is because this is a vertical displacement. I easily could have left it as x, and many people do, but I want to remind myself that I'm talking about vertical motion now. I'm not talking about horizontal motion. Now initially, the object is not moving. Well, first off, it's located. We'll go ahead and say that y equals 0. We'll set as the ground. So it is at some positive position above the ground because we said the up was positive. And as time goes on, it's going to start slow. So it's going to have a very small, shallow slope. And it's going to steadily speed up. So the slope is going to get steeper, steeper, and steeper. And additionally, since the acceleration is down, which means that the acceleration is negative as I've defined it here, we should be getting a frowny face. And we'll get something that looks like that. That's just, remember, how the position of it is changing throughout time. It starts with a very little change, and then it quickly speeds up. And if we look at the velocity versus time graph, initially it is 0, but it's consistently moving downward, so negative, and it's going to go down, and the slope of this line, which would be the acceleration, which tells us that the slope would in fact just be g. But we can easily flip these. And in fact, we'll see many situations when we want to. So if I said down is positive and up is negative, well, how is that going to change things? Well, really, everything is just going to be flipped. Now, if I set for instance, this is still y equals 0 at the bottom. I'm going to start at a negative position. It's going to initially go slowly and then quickly speed up. I'm going to start at 0, and it's going to be at 0 velocity and then speed up, this time in the positive direction, because we've said positive is down. And once again, this will have a slope of g. Same graphs, just flipped because we've switched the sign of up and down. We really just need to be careful on which one we choose and be consistent. Well, now we've looked at motion graphs, but we can also apply kinematic equations to objects moving in free fall. Because once again, we have one-dimensional motion with a constant acceleration, the acceleration being g, 10 meters per second squared down. So here's an example. A rock is dropped from a height of 25 meters. How long does it take the rock to hit the ground? Okay, well, that seems pretty straightforward. And we can use, just like we have in every other situation with kinematics so far, the guess method, givens, unknowns, equations, solve, substitute, in order to find the answer. So let's start off with givens. We have a few different givens here. Specifically, we know that the initial velocity is going to be 0 because it's dropped. The acceleration is g, which is 10 meters per second squared down. Notice I didn't write positive or negative yet. I just wrote down. And notice that delta y, the change in y position, because it's going this way, it's starting at 25 meters and then going downwards to the ground. So it is 25 meters down. Once again, I just write down. My unknowns would be the final velocity and the time, but we're trying to figure out how long, so that means we want time. I don't care at all about this one. Go look at your 4 kinematic equations, and we'll see that the equation that is best for this situation is delta x equals v naught t plus 1/2 at squared. But I'm just going to replace delta x with delta y. It's the same exact equation. I've just briefly changed the symbol to make sure I know it's a vertical displacement. I now simply need to solve for the time. And this may look a little annoying. But what we need to remember is that if I do this here, because v naught is 0, I can just automatically get rid of this whole piece. And that's going to make my derivation of my t much, much simpler. Otherwise, I would have to do some sort of quadratic formula, which I can do, but why make myself go through the hassle? And now that I've gotten rid of that first part, I can pretty easily solve for t. I'm going to multiply by 2 and divide by a. So 2 delta y over a equals t squared. And I'm going to take the square root of both sides. So I'm going to end up with the square root of 2 delta y over a. So something like that. And now, I went ahead and put the answer here, but I'll go ahead and plug my numbers in. And this is where down and up suddenly matter. And the reason why is because it depends on, or you define it as positive or negative. For instance, if I say down is negative and up is positive, I would say this is the square root of 2 times, well, this is 25 meters down, but that's negative, so it would be negative 25, divided by a, which is 10 meters per second squared down, which is also negative, so that would be negative 10. So if I do that, I would have 2 times negative 25 divided by negative 10. The negatives cancel, so that I have the square root of positive number, and I get t is equal to 2.24 seconds. If I had only done negative on one of them, I would have gotten the square root of a negative number, and more than likely you'll catch that mistake, but you may be able to get a little confused and a little lost. Additionally, let's say instead I said up was negative and down was positive. Well, then these would both just be positive numbers, and I get the exact same answer. As long as we're consistent, it does not matter. Now, the other one-dimensional free-fall situation we have is throwing an object straight up and down. Now, quick note, if you look at this picture over here, I know it looks like it's not coming perfectly straight up and down. It looks like it's moving a little bit to the side. That's just because it's very difficult to draw, on a two-dimensional surface, something in front of itself. So when you see something like this, we can assume it means really just straight up and down. Now, what we know already is that, remember, as long as it has left our hand and is in the air, a is equal to g, which is equal to 10 meters per second squared down. Additionally, we know that the velocity at the very top, at that instant, is 0, because what is happening right here for an instant is it stops and then it changes direction. Initially, it is moving in the upward, let's just say the upward direction. Here it slows down, briefly stops, reverses direction, and starts to speed up in the downward direction. So once again, I could draw some motion graphs for this situation, and we'll once again say that y equals 0 is the ground. And if I look here, this looks like a lot of motion graphs I've done before, where initially we are moving up and slowing down. So it's going, now let's be careful, we set up as positive and down as negative, so I'm going to say positive, negative. It's moving upward with a positive slope and getting shallower, stops for an instant, and then starts to speed up in a negative. And we get something looking like that. Additionally, initially it has a positive velocity, and then goes through. This is the instant it turns around, and then starts speeding up in a negative. And once again, my slope will just be g. Now in this particular situation, that is negative 10, because we said down was negative. But I easily could have just switched them again. I could have said that up was negative and down was positive, and we'll see that once again I get the flip, that initially it is speeding up, slowing down in a negative direction, then speeding up in the positive, and now I see my acceleration is positive, because I've now defined down as positive, and once again, the slope is g, but this time it would be 10 meters per second squared, not negative 10. So let's do another example to make sure we're all on the right page. And in fact, if you want to try and do this one yourself, that is perfectly fine. Just pause the video, try to do the guess method with what I've given you here, see if you can figure it out, and then come back in a second and see how exactly you did. Okay, let's go ahead and solve this all together. So a ball is thrown straight up with an initial velocity of 20 meters per second. How high is it after 1 second? So I'm going to go ahead and first write my givens, which the initial velocity is 20 meters per second up. Notice that up, really important. Time is 1 second, and a, which is g, is 10 meters per second squared down. Now one thing I want to note is a lot of people go, well, wait a second. How is the acceleration g? Because you were throwing it. And how can it be g at the end? Like, if it hits the ground, how is it g at the end? When we are talking about problems like this, we are really only looking at while it is in the air. In other words, we are saying our situation starts at the instant I let go. As soon as I let go and only gravity is acting on it, that's when we start. And when it comes back to the ground, we stop the instant before it strikes the ground. So in that entire span, the only thing acting on it is gravity, so the acceleration due to gravity applies to our entire scenario. Okay, our unknowns would be the final velocity and delta y. We don't care about that, delta y being our displacement. We see our equation. The best one would be delta y equals v naught t plus 1 f a t squared. Luckily for us, we are actually solving for delta y, so we don't even need to rewrite the equation. All we have to do now is plug numbers in. And once again, though, remember you have to be very careful with positive and negative. Let's say I make this positive and down negative, then v naught would be 20 meters per second up, so that would be positive 20 times 1 second, plus 1/2 down is negative, so that would be negative 10 meters per second squared times 1 second squared. And if I plug those numbers in, I get a displacement of about 15 meters. It has gone 15 meters up after 1 second. But remember that positive and negative are important, because let's say you made these both positive or both negative. You're not going to get the right answer. You have to be very, very careful that you are consistently defining up as one, positive or negative, and down as the other. That is easily the biggest mistake people make with these sorts of problems. Now, what I want you to do, let's actually just quickly note, you easily could have defined it the other way, and I could have said up was negative and down was positive, and if you do that, you can go ahead and try this again. We would just make this negative and this now positive, and if you plug the numbers in, you'll see you get the exact same answer. It does not matter as long as you're consistent. Though, in that situation, this would be negative 15, because it had gone 15 meters up. So what are the takeaways we have for free fall? Well, one, can we recognize which objects fall faster in a vacuum? That's a trick question. They all fall at the same rate, 10 meters per second squared down. Whether you make that positive or negative, that's up to you. Can we draw motion graphs for objects experiencing one-dimensional free fall? And can we apply the kinematic equations for objects experiencing one-dimensional free fall? Remember, the number one thing you need to recall is that positive and negative can be up or down. It does not matter as long as you're consistent throughout the entire problem.